Hey, good morning, good afternoon, good evening, wherever in the world you may be. I am Safwan Masri, Executive Vice President for Global Centers and Global Development at Columbia University. And it's really wonderful to be welcoming you here today for this extraordinary webinar, which is part of our book series in conversation with a joint collaboration with our partner, Columbia University Press. The series gives our global audience an opportunity to listen to and engage with scholars and academics, offering a variety of perspectives as they discuss the latest books. Our partner, Columbia University Press, was founded in 1893, making it one of America's oldest university presses. It publishes, translates, and distributes books in an array of disciplines and professional programs. The global centers, by way of introduction, are located in 9 countries as Columbia's physical and intellectual infrastructure in the world. They facilitate and curate research and education programs that connect us with local partners and serve to advance the creation and exchange of knowledge globally. Now back to why we are assembled here today, which is to discuss an incredible book, Music, Math, and Mind, The Physics and Neuroscience of Music, by David Sulzer. I will note that the title, while accurate, belies the wildly entertaining and genuinely humane nature of the book's contents. I had planned to read a quick excerpt by way of introduction, but it is almost impossible to isolate a paragraph in this propulsive book in which apparent digressions soon reveal themselves as part of the larger narrative. Technically, of course, there is no narrative. This is a beautifully structured scientific work in which the mathematics of music, pitch, scale, harmony, and rhythm, and the mechanisms of the ear and neural pathways are mediated through the experience of listening. But the technical aims of this book are buttressed by another form of listening, a kind of historical storytelling that unites across centuries and cultures. For example, the introduction of the book notes that the approach to contemporary musical education is rooted in a system developed to train orphans and abandoned children in Renaissance Naples, so that they might learn a trade in the absence of vocational inheritance. I did not know that. Sulzer points out that the word conservatory literally means places to save children. This is an interesting intellectual nugget, but within a few sentences, it forms a revelatory backdrop to the music of today, created by talented youth in places like the Bronx or Harlem or Detroit, places where there is little or no public support for music education, where with no formal training and no theory and few resources, kids develop new styles from what is available to them. Sulzer effortlessly and coherently moves from Bach in the early 18th century to Public Enemy in the late 20th, and leads us into the science of sound. Using sirens and pipe organs and underwater earthquakes to explain air pulses and waves, we suddenly find ourselves capable of tuning a guitar and understanding diatonic scales. It stuns with sense, as the mathematics are made both plain and engaging. There's a wonderful practicality and real-worldness to this book, underscoring its point that the physics of sound is a universal language, one that resonates deep within the structures of the individual brain, while providing diverse paths of connection throughout humanity and into the natural world of songbirds and insects and whales. Now to introductions. David Sulzer is a professor in the departments of psychiatry, neurology, and pharmacology at the Columbia University Irving Medical Center. His laboratory has made important contributions to the study of brain mechanisms involved in autism, Parkinson's disease, drug addiction, and learning and memory. He is also a composer and performer under the name Dave Soldier, and he has worked with many major figures in the classical jazz and pop worlds, appearing on over 100 records. Some of Dave's projects bridge music and neuroscience, including the Thai Elephant Orchestra, an orchestra of 14 elephants in northern Thailand, and the Brainwave Music Project, which uses electroencephalograms, I practice, of brain activity to create compositions. David, welcome. You're amazing. This is really terrific. There's much to discuss, and who better than Corina de Fonseca Wolheim to moderate? Corina is an award-winning music critic and cultural entrepreneur dedicated to helping people become better listeners. We would all benefit from that. From 2012 to 2021, she was a contributing classical music critic for the New York Times. Corina is the recipient of the 2021 Virgil Thompson Award for Outstanding Criticism and a 2018 residency at the American Academy in Rome. In 2019, Corina founded Beginner's Ear, a program of transformative listening experiences, which has brought live music mediations to diverse audiences and spaces, including a yoga loft, a sunken garden, a federal detention center, a dance studio, an independent high school, as well as more traditional music venues. Welcome, Corina. Welcome, David. Corina, I turn it over to you to start the discussion. Thank you.
Thank you so much for those introductions, and thank you everyone for tuning in wherever in space and time you find yourselves. And I'm so excited to just spend this next hour diving into what is really one of the kind of paradoxical pleasures, where something that we perceive so often as being really specific and personal, which is our relationship to music, kind of intersects with laws that are more universal and scientifically grounded. And there are really very few people who can speak both to the practice and the theory, as well as David/Dave in his composer incarnation. So it's really a treat and an honor to be here and get to ask hopefully some really basic questions to some really difficult and fascinating subjects. I was wondering, David, whether I could maybe start out by just asking you how your relationship to music and sound was born. Like, do you have an earliest memory around sound or even acoustics, like the phenomenon of music and sound in your life?
Well, first, thank you, Corina, for doing this, and Safwan for that great introduction to both of us. Well, I kind of can remember the first music that really, really moved me and made me want to be a musician. And that was my dad. He died quite young. I was 13, he was 39 when he passed, but he was a big music fan. He played the harmonica, and he played me Porgy and Bess. And I don't know what it was. And maybe it's, partly being, Ashkenazi backgrounds. And so it mixes together African-American traditions like James B. Johnson with these Russian traditions like Tchaikovsky, but whatever it was, it just killed me. And I just decided I want to be a musician. And I've had those sort of epiphanies a few times throughout my life. I remember very clearly being 13 and hearing Bill Monroe for the first time, the person who founded bluegrass. And I remember the song Stony Lonesome. And it was the most beautiful thing I'd ever heard. And then when I was 15, hearing Eddie Palmieri, who's still around, magnificent composer and band leader here in New York of salsa, and hearing his arrangement of his song Puerto Rico. And I also remember, I guess teenage years are particularly important for musicians, but also when I was 15, they let me into the bar and I heard Miles Davis play this extraordinarily aggressive electronic music that was like part Stockhausen and part whatever you want to call Miles, and really loud and really nasty and aggressive in this little tiny bar with only 40 people. And that was not, and so I've had, I guess, that feeling of just Any word sounds cheap. Transcendence, that suddenly the skies have opened and you understand something you never understood before. I do remember that when I was a kid, from that early memory, and thank God sometimes it still happens now.
Yeah.
What about for you, Karina? Do you get that as a deep listener? Do you hear Pauline Oliveros and go like, that opened up my mind?
I mean, I have very early memories. My earliest musical memories is definitely my mother singing us to sleep, and she would sort of be outside the room ironing, and there was just something incredibly comforting. It was sort of just the definition of love and safety, was just sort of an unseen source of a voice. I also remember, I mean, just to get also into the fascination of sound and the physical properties of them. Across the street from us, there was this kind of abandoned lot which the town used to store sort of construction materials, and they would have these enormous round, I guess, sections of tubing for water or sewage. I don't know, but as kids we would play in them, and I remember entering these kind of spherical little slices, and the echo of our voices in there was just something that was totally terrifying, even though it was open to both sides. And the idea of just sound creating a sense of, so I was just saying with my mom, it was like a sense of safety, but here, like the sense of strangeness and alienation was actually purely a function of acoustics. And so, like, I've always been fascinated by those kinds of phenomena, but unlike you, I rarely have the physical explanation for them. So I was wondering, because as a writer, I often find that I pick topics that I want to know more about. And as a journalist, when I write, and like with this book, were there questions that you wanted to answer? Were there like things that you didn't yet know when you tackled this project?
Absolutely. I just, when we were kids, we played in abandoned coal mines, which sounds really horrifying now, but that's what we did growing up in the Midwest. In Carbondale, Illinois. Carbondale's named that because it's a coal mining town. Yeah. And we had, a quarter mile away from the house, we had abandoned coal mines. And so the kids, we that's where we played. It's really dangerous. It's true, but that's what we did. So I don't know, that it was kind of, your story was reminding me of that. But your question, okay, there were a lot of questions I had. And I figured that the same kinds of questions that I have, other musicians have and other music fans have. So absolutely. One reason I started teaching this course at Columbia that's related to the book, and also the book, was to make sure I'd go through those things. Also, a lot of I had sort of a idea, kind of a fuzzy idea. I think this is common amongst musicians. Like, we know the well-tempered clavier means something. We know that there's something called well temperament, but exactly what is that? And can we understand it? And is it going to help us appreciate that music more? And so I wanted to know that for myself, but also I'm sure, and there's no doubt that these kind of questions show up to other people who are practicing music or people who really love music. So to have a place that would just kind of explain that clearly. And I felt that there is a similar book, but it's from the 1800s. So it's by von Helmholtz. And it's, I love that book, and I've been reading it over and over again for many years. And it's been a very influential book, both for scientists and for music. However, it's not a very easy book to read for contemporary readers. And it's also, it's written during the American Civil War, and a lot of has happened since then. So that's why I felt it was necessary, both for myself and for my imagined audience of other musicians and music lovers, to work on this project.
Yeah, and I mean, of course, to some people, the idea of music and science seem almost like like very far apart, one belonging to the world of arts and the other to sort of hard facts and measurable things and theories, and yet they've been integrated for a really long time, right? And I think one of the chapters that you go into is about one of the oldest questions and sort of utopian hopes that people had, which would be that there would be this single law that would explain the movement of the spheres of the planets, the movement of the universe in musical terms. That kind of idea that I think Leibniz called, music as the hidden arithmetic of the soul. And so I'd love to have you maybe like dive into that to give our listeners like an example of where these theories came from and yeah, what the story is behind the music of the spheres.
Well, the music of the spheres definitely goes back to Egypt, China, Mesopotamia, and I'll get there in a sec. But I wanted to mention for you personally that, and this is something that I only realized in the last week or so, reading a new biography of Bach. He had a club called the Society for Musical Sciences, and among the other members were Telemann and Handel. And they would send each other packages of their new handwritten scores and their new ideas, because they were involved at that time. They called it musical sciences for a reason. It wasn't only the well-tempered clavier, which was a big one in the history of what we call classical music now, allowing, it's proving that you could write in every key. And that sounds, I mean, any contemporary musician who plays Western music now says, of course you can play in any key. But at the time, it wasn't clear that you could do that, in part because the tuning system was different. And if you play a C chord on your clavier, that would sound good. But if you play an A flat, it would sound kind of out of tune. And it just wasn't clear that you could do this. And that was some of the math that these people were working on. So when we think now, these great composers of the past, they just wrote by completely without an understanding of the tools of the math that underlies. I mean, it's not quite true. I mean, of course, you have your organ or your whatever instrument you're using. You're playing on it, and you go like, this chord sounds good, and that chord doesn't, and that's kind of empirical. And I suppose it would be the kind of artsy idea that you just do everything by intuition. But it's not precisely true. It's only part of the truth. They were really trying to figure this stuff out. So regarding the idea of the music of the spheres, I mean, that does go back for a long time. And Pythagoras didn't leave any writing, so we only know it's sort of like Christ, we have to go by what the gospel said, but that were written by people that may not have even known him. And but the idea was out there that we would reach some kind of perfection or elegance of understanding the universe. And at that time, music was one of the sciences, along with, topography, and they had a list of what the sciences were. And music was one of them. So I guess it's continued to be a source of fascination for people. The idea that you should be able to explain the universe in simple ways based on music. And Shakespeare referred to the music of the spheres, and there have been plenty of books about it during the Middle Ages, but the classic one is definitely Kepler's Harmony of the World. And boy, I'm going to try to compress this, because I could talk for half an hour on this and everybody's going to drive everyone insane. But so Copernicus had decided, I can describe the orbits of the planets much better if the planets move around the sun. Okay. And Tycho Brahe didn't exactly like that idea. But he had to say, well, something interesting must be happening. Because if you look at Mercury, so Tycho was the best of the astronomers. He had very good eyesight. And his protege, Kepler, had very poor eyesight, was nearsighted. Never so much of an astronomer, but better at trying to derive math that might explain the universe. So Tycho would say, look, if I follow Mercury, it's following in a circle. Well, that makes sense. But wait a minute, it's going retrograde. So if you're into astrology, you still talk about Mercury going in retrograde. But it is going in retrograde from our standpoint here on Earth. Now, how can that happen? It's very hard to explain that. So Tycho came up with these ideas, and he said, even on his deathbed, so he died unexpectedly, and he's telling his protege, Johannes Kepler, please don't let me die in vain. Please explain to everybody the math of how the Earth is still, Copernicus is wrong, the Earth is still the center of the solar system, but the planets are moving like this in curlicues around it. So that would explain when it's going this way, it would be appearing to go retrograde, okay? So that should make sense. Kepler spends 20 years trying to prove his mentor correct, can't do it. So he says, well, maybe Copernicus is right after all. But when he plays the notes that correspond to the different planets, and the way that may not make sense right now, but if you take a string, and I happen to take this, this is a tie instrument, but it doesn't really matter. So you take a string, and now you fret it. It's a higher note. As a violinist, of course, you intuit that. And if you do it exactly at the halfway point, wherever that would be here, but we're going to get a harmonic, and that's a precise octave. So the inner planets, like Mercury, have a much, if you made the string the length of the orbit and play that note, and then you play it along with Venus's orbit and Earth's orbit and Jupiter and Mars, they're not in tune. He said, there's no way that the master artisan of the universe would make an out of tune universe. It can't be true. So what is it? He spent a few more years, and it's all in the book, which is not an easy book to read, but a lot of fun, especially if you're into really esoteric stuff. And you'll find that he was able to explain it by saying, the planets don't move in circles, they move in ellipses, which means once in a while, they're all in tune. Maybe they were playing a major triad and perfectly in tune at the time of creation, and we're just kind of waiting for them to line up. And once in a while, you get them in tune again. So, yeah, this seems nuts, but it is the basis of modern physics. It is the basis of, Newton read the book. He said, well, we have to explain this on a physical basis. To do this, he and Leibniz came up with calculus. They came up with force and the understanding of gravity. And that led to what we're doing right now, which is the astonishing ability to have a conversation from far away. But it was based on a musical idea.
And so, I mean, just explain to us the idea of music, first of all, seems to require sound, right? And at its most elemental, we're talking about frequencies, right? Frequencies of vibrations, and we're talking about ratios. Like you were saying, the length of a string, once divided, produces the same note, but up an octave. And there are other sort of whole note ratios that produce the most elemental building blocks, the fourth and the fifth. And I'm sure we can get into the more nitty gritty of that too. But so as I understand it, like one of the ways to even think about music in space, and people still think about it, and I think there is recent research about it, is to sort of translate some of the frequencies of, for example, the rotation of a planet, and then against its orbit. And then you start having, I think in some cases, exactly these whole note ratios again, that sort of seem to map onto musical intervals. And so I'd be curious to know, like, what are some of the more recent studies, and how does one even study the idea of sound and music in space?
What a great question. Okay, so you're right. And Kepler realized there was no air in space. He says it in his book. But he's saying, but if you were sitting in the sun, and he was too Catholic to say God sits in the sun, because that's not part of the doctrine. But he believed it, so he had to write it. He was very careful about how he wrote it. Then whoever is sitting in the sun would perceive these as sound even without, which makes sense, because after all, we do pick up these frequencies. I mean, it doesn't make sense. If you were out in space, you wouldn't hear anything with your ears. That may be true. But if you could perceive the frequencies, and after all, we do that, yeah, you're going to see that you're going to see the frequency relationships, including the notes. So I do cite a couple of instances in the book. For instance, there are pulsars that travel around each other, or there are binary star systems that travel in harmonic ratios. So they're traveling in, between a do, re, mi, fa, so, a do and a so, a perfect fifth. There are other ones with other so-called harmonic intervals, and there are other things which are vibrating throughout the universe. For instance, there's a big gas cloud, which is vibrating at 57, I think it's 57 octaves below a B flat, which is sort of permeating our galaxy. So, and every once in a while, people come back to Kepler and try to re-explain it. He had 6 planets. Now we have who knows how many, right? We can't even agree what a planet is exactly. And so we have to constantly go back and see if they're doing that. And I'm supposed to have dinner with Lee Smolin, who's a physicist, next week. And I believe he's writing, he and a mutual friend, Jaron Lanier, I think, are writing a new paper that's supposed to explain their new version of Kepler or something like that. But people still use that as a jumping off point. Okay, you could see I'm a little sarcastic about it, but nevertheless, it leads to these kinds of exercises, and these kind of conundrums can sometimes really lead somewhere, including the foundation of modern electronics, physics, and things like jet propulsion and travel to outside of the Earth. So, and we still have to do that math now. If we're trying to aim where, like right now, we're putting up a new satellite that's going to be very, very stable. And it ends up at being one of the 2 foci that Kepler said we need to have. So one of this is the sun, the other one's nothing, right? And that's what you need to draw an ellipse. We're actually sending a satellite there now. That's going to be a very stable, very long-lived satellite that will work as an ideal observatory. So we're still going back to that stuff now. So sometimes maybe it's good to challenge yourself with things that don't. Things like, well, we know there's no air in space. It shouldn't work. Yeah, it shouldn't work. But let's use this as a way to take off with our imagination.
Yeah, and I mean that idea of trying to retrofit a theory to an aesthetic ideal, I think that's like so fundamental also to a lot of sciences that, at heart, like we respond to things that are elegant and in some way harmonious, whatever that means, right? And I think it's not an old-fashioned idea, like it sort of still is a pretty good principle by which to at least investigate things. And I thought that might be a way to lead over into another debate that at one point in European history exercised like some of the greatest mathematical minds, which was the idea of temperament, which is related to tuning, right? And like, could you talk us through, like, as a sort of really basic 101 course into what it is and why it became such a sort of cause célèbre for scientists?
It's still a cause célèbre now. We still don't have ideal tuning now. And one of the questions, so I put a series of questions throughout the book that I know musicians care about. And one of them is this thing that you hear people say all the time: you can't actually be in tune. Is that true? It actually isn't. It is true. Now, we can get, people haven't quite gotten there yet, but we can be more in tune right now than we have. And just, I'd give a shout out to young English composer Jacob Collier, who has plenty of YouTube videos, but people might want to check him out because he's figured out a pretty good way to be in tune as you move through frequencies, even with traditional harmony. So saying we're not in tune, I understand that doesn't make a lot of sense to people, but I'll try to say as simply and as rapidly as I can. So the ancient scales were probably very similar to pentatonic scales, 5 notes per octave. And the way that we know this the best is by recovery of ancient instruments. So there's a set of flutes from Germany, another one from China. They were made out of bird bones, so that's why they survived. The other instruments didn't. The ones in the caves in Germany, which also are in the same caves as the first recovered figurative sculpture, are about 39,000 years ago. And a couple of them are in pieces, but one of them is relatively intact. And a artist archaeologist named Wolf Hein has reconstructed them, and they play pentatonic scales, not precisely the pentatonic scale that's used throughout the world right now, but very, very close. And the scale that we're referring to, and for musicians, it would be like C, D, E, G, A, okay? And that scale used in modes, we're not going to, I'm going to abbreviate this, but is the popular scale of most Chinese popular music, Thai popular music. I did this just for fun about a year ago. I sat and counted on American pop radio how many songs were pentatonic, and I got something like 80% of the hit songs are still pentatonic now, okay? So this is the most popular scale in the world. Bobby McFerrin does a little cute thing where he jumps on the stage and the audience instantly can sing pentatonically. So what's this made from? This is made, as you were saying, from dividing the string into pieces. Now, maybe it shouldn't be this way, and I don't think the Pythagoreans would have liked it, but the scale that I just told you is if you take a fifth and then another fifth of that and another fifth of that and another fifth of that and then stop, that's that scale, okay? Now, there are a lot of issues with that scale depending upon the style of music, and the way that people address this in a large part makes our musical styles. So if you use the tuning of the blues, you're going to get a certain kind of set of things that sound good and work there. The same thing in these pentatonic songs. The same thing in Indian music or Arabic music. Indian and Arabic music both have a very advanced sort of mathematical basis. One of them uses 22 tones per octave, the other one 24. They still end up using, typically a rag will have 8 notes per octave, very similar to Western music. Now, how is all that stuff set up? And how did it now become the most popular worldwide tuning system, which is dividing octaves into exactly precise 12 notes? Well, if you do it precisely, and I won't go into the math, but you can understand it in 5 minutes. And you know, you can go through, anybody who's gone through, who knows how to multiply and divide can, I'm not trying to advertise my book, but just you read that chapter, steal it, I don't care. I know the publisher's putting this on, but read that part. It will take you 5 or 10 minutes of concentration and you'll understand how it's done. When we set it up as a series of this harmonic and then a daughter harmonic on top of that and a daughter harmonic on top of that, they don't work out to come back precisely to the same place. Classically, that's a number. It's called the Pythagorean comma, and it's very similar to if you do 4 times 365 days, you're not quite lining up at the same part again, and you have to have a leap year. It's very, very similar. So we've done that with the tuning system that's used in synthesizers and so on around the world. Trouble with that is a lot of it is clearly out of tune. Now, we're not used to thinking of it as out of tune because we're growing up with that system. Nevertheless, you hear Indian classical music and you will hear that there's a certain kind of calm and beauty and sort of shininess according to the top, where you hear these notes playing with each other, and it gives a very satisfactory sound. Okay, this is very hard to do, essentially impossible in the way that we tune right now. We're not going to be able to build up all those harmonics, but we're trading off so that we can move through keys easily. So is this problem soluble? Well, it kind of is now, because when we had, so the early people that were working on piano didn't know how to solve this problem. They were very aware of it. And one of the reasons that medieval music and Renaissance music sounds so different to us right now is because they were writing for the chords that sounded good on their keyboards. Then with the advent of Temperament with Bach and then later smoothing it out even more, or roughing it, if you would rather, to 12 equal. Now you can move keys instantly. You can be a romantic composer. You can be Duke Ellington or George Gershwin, and you can just jump from this key to that key and not even have to think about it. You didn't used to be able to do that. But the trouble with that is it's out of tune, even according to our ears. With new technology, we should be able to do it, because of piano, you can't stop to retune the notes all the time. But with better computation, we should and are starting to move to, okay, I'm in the key of D flat, I'm going to move to the key of F. I want this to be in tune now. Boom, boom, boom. Let's have some very fast analysis and change the frequencies, and now we're in tune. So I've started doing that a bit. Other people are starting to do that too. It'll be interesting. It will be interesting. Another case of having where the musical idea actually precedes the technological advancement. We're going to make this technological advancement because we have to, in order to play the music that musicians want to be able to play.
Mm-hmm. Well, I thought it was fascinating that you touched on the fact that it doesn't sound out of tune to us because we've been conditioned, because we've grown up in this essentially imperfectly tuned musical world for a few hundred years now. And so there are different, like each musical language and grammar sort of sensitizes the ears differently, right? And I imagine that if you grow up in a place where there are 24 notes to a scale, you have a more sophisticated sense of hearing pitch than somebody who's used to the 12.
Well, you're right. And people from the Arabic classical traditions and the Farsi tradition, and I've performed with them. And if you think you're playing an F, and it's actually between an F and an F sharp, and if you don't play that exact, they'll just stop the band. It's like playing with a jazz group where the groove gets out and the drummer just goes, you stop, and
we're done.
And they sing it and they go, it's not and they want to make sure, and if you don't do that correctly, you're not conveying the music correctly. We Americans do that too with blues, right? If you don't play the blues note, which is not on the keyboard, right, you don't play it the right way, it sounds silly. It doesn't work. And the way piano players get out of it is like, if you're in the key of C, you play the E flat and the E together in order to get that note that's not on the keyboard. Right? If you don't do that, you're going to drive people crazy.
I love that you bring that up, because that gets into something that you also touch on, which is the fact that the sort of the crunchy and the friction and the imperfect in music, imperfect in the sense that it's not perfectly consonant, and it's not like this perfectly kind of glassy, yeah, balanced, kind of harmonious sound are the things that we're drawn to often, like as expressive or as interesting or as stimulating in sound. And one of the really fascinating parts of your book is where you start getting into the physiology of listening and hearing. And you also draw on studies done on animals. And so I would love to hear how we talk a little bit about like how we respond to dissonance and consonance and where we can measure those things.
Yeah. Okay. So it seems likely right now that first, for most animals, and essentially animals with brains, there are very similar ways to the way the ear works. I mean, there are differences that, for instance, we hear to 20,000 hertz and bats can hear to 200,000 hertz. But the operation of the eardrum and the operation of the neurons, which are called hair cells, which are the ones that do frequency detection, are very, very similar. So I'll say with essentially all the mammals, they're similar, but they're even similar for insects, some insects, and for birds, for reptiles. So the way that we hear, when you get into specifics, yeah, there's some differences. Elephants hear an octave lower, whatever. But the pathways are very similar. The way the hair cells work, there's some differences, and there's some animals that are better at mapping a particular frequency than us, and other ones which are worse. Like crustaceans aren't particularly good. Those crustaceans which can hear, but a lot of it's still very similar. And for those animals that have a cortex in the brain, auditory pathways look to be very, very similar. So the best we can tell from sort of anatomy and physiology, by physiology, what I'm referring to is how neurons react to sound. It looks like most of the animals we think about hear very, very similarly to the way that we do. Mm-hmm. Will they hear consonances in the same way? Well, it certainly looks like they do. There's also some evidence in that animals who sing will often go for these consonances. And then in the little bit of work that's been done on this kind of thing, I've done some of it. You have elephants who play instruments, or pygmy chimpanzees, bonobos, who play instruments, or birds who might play instruments. It's not a lot of work's been done on it, but for people who are around them, realize they often go to consonances that sound like consonances for us as well.
Mm-hmm. Yeah, and I think before we hand over some questions to the audience, and I can see that some of them are gathering in the chat, which is fantastic. I do think we have to address the elephant in the Zoom and ask you about your work with these elephant orchestras, and see what would be your approach to answering the question, is it music that they're making, and is there creativity in it, and what are the arguments for saying yes or no to those questions?
Yeah, so so for the listeners, so we started building giant instruments for elephants in northern Thailand 21 years ago, year 2022, and by doing that and by working with the elephants, I could find what elephants like to play and what they don't like to play. And I went in there, so I spent some time just going around northern Thailand first, trying to decide what the instruments were going to be. The music up there, we've already referred to that, is pentatonic music. And the elephants, these are not wild elephants, these are domesticated elephants. They're around 1900, there were 100,000 domesticated elephants in the country of Thailand. Now it's between 3,000 and 4,000, so it's a much smaller population. And they are often surrounded by music, because the people where I was, which is the Thai Elephant Conservation Center near Lampang, when I first went there, there, it was, not every place had electricity. The restaurants didn't have refrigerators, usually didn't have walls, and of course, in the last 20 years, it's become very, very built up. But people made their own music, including that instrument that I pulled out. They would play that instrument. And so the elephants would hear that music all the time, and they play it for the elephants. And when you bring them in from the forest at night, you sing to them. So people knew very well that elephants like to listen to human music, but would they play them? So building the instruments and scales that they grew up with, which happen to be the most popular scale for humanity too, just go back a few minutes, we were talking about it. They enjoy playing on that scale. And one of the things I discovered was we had a kind of brilliant marimba player named Pratida, who at the time was 7, but that means now she's 27. And so she was very good at playing it. And I put in a note that definitely sounds out of tune, if you will, dissonant to us. And she hit it once and she avoided it. Then she kept playing, and she was just playing fine with nobody telling her to play, just playing. And then after about 5 or 10 minutes, and we actually have this on video, she went back to that note and played it over and over and over again, while the other notes are still ringing, as if she was finding the pleasure. Now I'm projecting, but that's the best I can do. She's finding the pleasure in hearing that quote dissonant note and how it kind of played with the other notes, which were all kind of, very soporific perhaps, and all kind of sweet and nice. See like that one.
That is an astonishing and fascinating story, and maybe a good place at which to just maybe turn it over to our audience, because I see a bunch of really great questions. Should I, maybe I'll just read out a couple.
Yeah, if you can, from them, yeah. Go ahead.
Jennifer Chong says, if there was air and space, would it be loud or quiet? And what sounds would we hear?
And would the stars be too far, right?
Stars be too far to hear them.
Can you say that question again? And I'm looking on my chat. I don't get the questions. I'm sorry.
So if there was air in space, would it be loud or quiet? What sounds would we hear? Would stars be too far away to hear them?
That's a very poetic set of questions. How far can vibrations go? Vibrations can move across the universe. So we would, and they move at the speed of sound, but the speed of sound is based on, among other things, the density of the air. So the questions you're asking actually are answerable, as poetic and odd as they may sound. And you could sit there for half an hour with a calculator or an Excel spreadsheet, and you could actually come up with the answers to your questions. But you should be able to hear sounds from the edges of the expanding universe.
There's also, a book that came out just last year called Alien Listening. Did you know it, David? Have you seen it? It's by 2 music theorists at Harvard, I think Daniel Chua and Alexander Rading. And it goes into a lot of questions about music and space, and the Voyager record, and what aliens might do with it if they ever found it. So it tastes
good, right? Yeah, you know, go play, yeah.
If they knew to listen to it rather than eat
good nutrients, yeah. Speaking of which, Laurie Spiegel, who's a local New York City I'm sorry, Laurie, I don't mean it that way, but one of the pioneers of synthesizer music. Her piece, which is meant to be a modern realization of Kepler, is on that record.
Mm-hmm.
And so I just wanted to give Lori Spiegel a plug there. Please go ahead, Corinne.
So Milton Schinberg is asking, or is relating, I was playing piano to accompany my almost 2-year-old grandson's singing. I was shocked to find he was singing right on C major. Is C major the most, quote, natural key?
No, absolutely not. No, that is interesting, but I'm guessing that he heard something that you did in C major, or some, kids can have perfect pitch. He may have remembered C major from something else, but the do or the saw is completely arbitrary. There is a reason that we came up with C where it was, but in the Renaissance and the Middle Ages and Renaissance, you would go from a low note, which we now call G, it's the low G on the organ, up to the C above the staff. This was called ut, and this was called gamma. So when we say the gamut, you run the gamut. It's literally from the lowest note of the Renaissance scale to the highest note. But like with Indian classical music, it could move to any frequency. You just found the place where you're comfortable, and that you would call C. But it's not like it was 240 hertz. It could be anything. And Indian classical music still does that. Their do, sa, it can be on any note, depending upon the instrument you're playing or where your voice is strongest.
And I think people have pointed out that even our idea of what a C major is not the same as it was in Beethoven's time, because the pitch of the A has changed, right? So Beethoven's Fifth Symphony in C minor is kind of in C sharp minor to his ears now, but that's a whole different
yeah. It's something they still tune about 4 cents sharp in Europe compared to classical ensembles over here. That's true.
So here's a great question. David Vilkomerson is asking, what is the scale that birds sing in?
Well, that's a tough one to answer. Of course, it depends on the species. There are a lot of thirds, fifths, and octaves in birdsong. And there are also songs that sound more mellifluous to us, and mellifluous to birds is something different, but there's some work that can kind of say that. And typically birds like to listen to music of their own species the most. And the reason we say that is not just behavioral experiments, but also recording from the brain. And there's a good amount of work on that. It's mostly in zebra finches. And zebra finches to us don't sound particularly musical. However, Ofer Chernovsky here, again in New York at Hunter College, can show you if you just slow them down, it's for us, because Ofer will tell you that songbirds look at us like we're really stupid. We're really slow. That's why you can't catch them. They're just like, we're ridiculously slow beings just working on really boring stuff. And if you slow them down a lot, then suddenly it does sound like music to us. They just hear faster. They sing faster and they hear faster. So, but to us, those birds don't sound particularly melodic, yet they are. And so they will concentrate mostly on their own species, and they have a whole enormous variety of songs, very, very wide variety of songs. What's not been studied are these birds that have very wide vocabularies, like the mockingbird, which you can hear here. I hear mockingbirds. I go jogging here on the West Side Highway along the Hudson River, and there are mockingbirds there. And they have beautiful voices, and they sing many, many different songs. Many of them they steal from other species. Of course, the nightingale you're aware of because you're from Germany, and then there's the most extreme example, the lyrebird. So are they responding to many other species? Well, obviously they are. In fact, captive lyrebirds will even imitate human machine sounds. So I guess what I'm saying is when you're asking things like preference and scales, it's going to be very, very species dependent, and maybe personality dependent, individual dependent. Again, these even zebra finches, each one has its own specialized song. They can tell they can tell individuals apart. You have a flock of 25, and each one knows who the other one is and where they are because of their song.
Wonderful. There's one question that I really love, because I last year wrote an article also about music and deaf people and how they relate to it. Michael Schulman is asking, for those who are deaf, can there be visual representations of music such that those who are deaf can hear music? And I think it's a lovely way to bring up the question, to what extent hearing is essential for experiencing music.
Right. And there's a long history of composers who've been deaf and have continued to write. Of course, everyone knows Beethoven, but quite a few others, Dvorak, for instance. And there's I'm going to refer the questioner to the website of Richard Einhorn here in New York, who's a really brilliant contemporary composer, has written wonderful stuff, and is deaf and has been working on exactly these kinds of questions. And he is able to replace / reconstruct some of his hearing, but he's used a whole variety of techniques, and he writes very eloquently about this. So Richard's last name is spelled Einhorn, and I would certainly go to his writing. And there are some other performers. There's a famous percussionist who is so-called profoundly deaf, meaning that there is some hearing involved. One thing that, going back to the animals, are whales have ears, but they don't use them very much. Their perception comes mostly through vibrations that are picked up in the bones, especially in the face, and then are transmitted to the auditory nervous system. And of course, they sing a lot, and they can hear each other from hundreds of miles away. And they do this without ears. Now, some human perception is like that. And you know this as a violinist. You take a tuning fork, and then you put it on here, and then you hear it very soft. It's not going through your ear. Right? So it kind of depends on what kind of deafness you have. And there's a great deal of work on it. And there's things are getting much, much better in treatment of many kinds of deafness. Cochlear implants are still not great for a lot of music listening, I understand, but they're just taking leaps and bounds in technology.
But I think there's also a lot of very creative and empathetic work being done on using sign language to sort of transliterate some of the emotional and sonic content of songs, like in addition to the words. And like I saw this incredibly moving performance of the Bach St. John's Passion by a group called Sign and Sound, I think, where they had participants who were deaf, who were sort of signing like expressive elements that rendered some of the kind of the flow and ebb of the music, and sort of created something that was really inclusive in that way. I feel like we're coming to the end, but yeah, we're sort of at 12:59. I see more than one person asked about perfect pitch. Do you want to just address that fascination with perfect pitch?
Not really terribly understood. Virtually everybody that has perfect pitch grew up in a musical household. It's probably more common than we know, because if you sing a song that you know, you'll frequently start on the same pitch, even though you don't know what the name of the pitch is. So maybe that a lot of what we call perfect pitch is in fact just the ability to name the pitch, not that it isn't the talent of being able to find the same pitch.
This has been nothing less than amazing, really amazing. You know, I'm listening in awe. I think I understood most of it, but it's just fascinating. And I have so many questions, and I was tempted, Karina, before you went to the audience, to jump in with a couple of questions, but I said that would be unfair. but hopefully we will have other opportunities, maybe more privately, to discuss some of that. But this is great, and I'd love to hear you perform also, David, or Dave Soldier, I should say. And Karina, I mean, I have questions for you and about listening and the art of listening and music, and how those are often used, oftentimes successfully in bridging divides. And, I'm thinking, for example, about from Colombia, the great late Edward Said and the Said Barenbaum Orchestra, and that's a totally different, sort of dimension to go into. But let me stop because we are over time, but this has just been really nothing short of fascinating. And it's really been a pleasure watching and listening to the two of you have the exchange that you have. So thank you so much. Thank you to Columbia University Press, and, go out and buy David. Have it on your bookshelves, read it.
Don't buy it for my sake, but
Yeah.
maybe the press. And thank you for the shout out to Edward Said and Daniel Barenboim.
Yeah. Thank you, David. Thank you, Karina.
Thank you,
Thank you.
Karina.
It was a pleasure. It really was.
Bye.
Thank you, Safwan.